Picture this. February 1962, Colonel Viktor Petrova, Soviet test pilot who'd survived dogfights over Korea and pushed experimental jets past their breaking point, standing on the tarmac at Shenyang aircraft factory, doing something unthinkable in communist diplomacy. He was refusing to fly. The invitation seemed simple enough. Take one of these newly manufactured J-6 fighters for a test flight and provide your professional assessment. These aircraft were Chinese-built versions of the MiG-19, produced using Soviet blueprints, Soviet tooling, Soviet training. On paper, they should have been virtually identical to fighters Petrov had flown dozens of times. His response, delivered through an interpreter to increasingly uncomfortable Chinese officials, was firm, non-negotiable. Under no circumstances would he or any member of his delegation climb into the cockpit of these aircraft. What could make experienced Soviet aviators, men who regularly risked their lives testing cutting-edge military hardware, categorically refused to fly what appeared to be familiar aircraft? The answer lay not in cowardice or political posturing, but in what they had discovered during 3 weeks of intensive factory inspections. Their findings would document one of the most spectacular failures in Cold War technology transfer, expose the hidden costs of rapid industrialization, and contribute to the collapse of the Sino-Soviet Alliance. The gap between possessing blueprints and actually understanding how to build complex military hardware, that gap is measured in crashed aircraft and dead pilots. To understand why Soviet engineers refused to fly Chinese-built fighters, we need to examine the context of Sino-Soviet cooperation in the 1950s. The relationship between Moscow and Beijing during this period was complex, marked by ideological alignment, but also by deep-seated cultural differences and competing visions of communist development. When Mao Zedong visited Moscow in December 1949, seeking Soviet assistance in modernizing China's military, Stalin was initially reluctant. The Soviet leader had invested heavily in the Chinese nationalists during World War II and viewed Mao's communists with suspicion, seeing them as agrarian revolutionaries rather than proper Marxist-Leninists. Stalin kept Mao waiting in Moscow for weeks, a calculated humiliation that Mao never forgot. The eventual agreement, signed in February 1950, provided for Soviet technical assistance, but on terms that clearly established Soviet superiority in the relationship. The outbreak of the Korean War in June 1950 changed everything. Suddenly, China was no longer a distant ideological ally, but a critical partner in containing American power in Asia. Chinese troops poured into Korea by October 1950, suffering enormous casualties but preventing UN forces from overrunning North Korea. Soviet military aid began flowing into China on an unprecedented scale. The Soviet Union provided MiG-15 fighters that Chinese pilots flew in Korea, and Soviet advisors began arriving to help establish aircraft production facilities. This was the beginning of what appeared to be a comprehensive partnership in military aviation. The scale of Soviet assistance in the early 1950s was remarkable. Thousands of technical advisors arrived in China, bringing complete sets of industrial equipment, technical documentation, and training programs. Entire factories were established based on Soviet designs and organizational principles. Chinese engineers and technicians traveled to the Soviet Union for training at aviation institutes and manufacturing facilities. The goal was nothing less than the complete transfer of Soviet aerospace technology and manufacturing capability to China, creating a second center of communist aircraft production that could support revolutionary movements across Asia while reducing the burden on Soviet factories. It was an extraordinarily ambitious undertaking, perhaps the most extensive technology transfer program in history up to that point. It was built on assumptions that would prove dangerously flawed. Before we examine what went wrong at Shenyang, you need to understand why the MiG-19 was such a demanding aircraft to build. This context is essential because the manufacturing defects the Soviets discovered weren't minor quality issues. They were death sentences waiting to be executed at 1,300 kilometers per hour. The MiG-19, designated Farmer by NATO, represented a quantum leap in fighter design when it entered Soviet service in 1955. It was the Soviet Union's first production supersonic fighter, capable of reaching Mach 1.3 in level flight. The aircraft fundamentally changed how Soviet tacticians thought about air combat. To Tumansky RD-9B axial flow turbojet engines, each producing approximately 3,300 pounds of thrust with afterburner, gave the fighter unprecedented power. Swept wings at a 55-degree angle, and an all-flying tail provided impressive maneuverability for its IRAV, the culmination of Soviet research into transonic aerodynamics. The MiG-19 was designed during a period when Soviet engineers were rapidly absorbing lessons from German wartime research, while pushing the boundaries of what jet propulsion could achieve. They had studied captured German swept-wing data, incorporated insights from British engine technology that the British had foolishly shared in the late 1940s, and developed their own innovations in aerodynamics and control systems. The result was an aircraft that was temperamental, demanding, and absolutely unforgiving of manufacturing defects or maintenance shortcuts. Here's what made this aircraft a manufacturing nightmare. The fuel system fed to thirsty engines through a complex network of pumps, lines, and valves. Every connection had to be perfect. Single, poorly tightened fuel line connection, a single contaminated seal could turn the aircraft into a fireball. Soviet maintenance logs from the period document at least 14 MiG-19s lost to fuel system fires during the aircraft's first 3 years of service, and those were aircraft built in Soviet factories with Soviet quality control. The hydraulic systems operated at pressures exceeding 3,000 pounds per square inch. These systems controlled the flight surfaces that kept the aircraft stable at supersonic speeds. At Mach 1.2, any sloppiness in hydraulic assembly meant death. When you're flying just a few hundred meters above the ground, you need absolute confidence that your controls will respond instantly and precisely. There's no time for a second chance. The engines pushed Soviet metallurgy to its absolute limits. Turbine blades spinning at tens of thousands of revolutions per minute, subjected to temperatures exceeding 1,000 degrees Celsius, operating under extreme vibration and stress. The margin for error was essentially zero. If the metallurgy wasn't perfect, if the balancing wasn't precise, if the tolerances weren't maintained, the engine would fail. Sometimes it would just stop, forcing an emergency landing. Sometimes it would come apart violently, sending turbine blades through the fuselage like shrapnel. Soviet pilots called this eating the compressor, a grimly humorous term for an event that usually killed whoever experienced it. Soviet test pilot Major Georgy Mazlov, who set multiple world records in MiG aircraft, described the MiG-19 in his memoirs as a beautiful but temperamental mistress. She rewarded skill and punished carelessness without mercy. During the aircraft's development phase, several prototypes were lost, and several test pilots died sorting out its characteristics and identifying manufacturing requirements. By the time the MiG-19 entered serial production in 1955, these painful lessons had been incorporated into manufacturing procedures and quality control protocols. Soviet aviation factories knew exactly what could go wrong because they had seen the consequences in crashed aircraft and dead pilots. This institutional knowledge, purchased at the highest price imaginable, would prove impossible to transfer completely to China. But in 1956, nobody in Moscow fully understood that yet. When the Soviet Union agreed to transfer MiG-19 production to China in 1956, it seemed like a natural extension of socialist cooperation. The Chinese would receive complete technical documentation, thousands of pages of blueprints, metallurgical specifications, assembly procedures along with manufacturing equipment shipped directly from Soviet factories, and comprehensive training for their engineers and factory workers. In return, China would gain the ability to produce modern fighters domestically, reducing dependence on Soviet deliveries and building an indigenous aerospace industry that could eventually develop its own designs. The plan looked perfect on paper. Triumph of socialist cooperation and technological solidarity.
Yes.
But the agreement was built on a dangerous assumption that China's industrial base could absorb this technology. What nobody in Moscow fully appreciated was the enormous gulf between China's industrial capabilities in the SGA, the 1950s, and the requirements for producing supersonic fighters. China's manufacturing base had been devastated by decades of war and civil conflict. The Second Sino-Japanese War from 1937 to 1945 had destroyed much of China's limited industrial infrastructure. The subsequent civil war between communists and nationalists had further damaged what remained. When the People's Republic was established in 1949, China's industrial capacity was concentrated in Manchuria, where Japanese occupation forces had built factories to support their war machine. These facilities had some basic machine tools and manufacturing capability, but they were designed for relatively simple production tasks. The country had virtually no experience with jet engines, no tradition of precision manufacturing at the levels required for modern aircraft, and a workforce that, while enthusiastic and hardworking, lacked the technical training and industrial discipline Soviet factories had developed over decades. Soviet factories by the 1950s had evolved systematic approaches to quality control, standardized training programs for specialized skills, and established procedures for documenting and solving manufacturing problems. Workers were organized into specialized teams, each responsible for specific aspects of aircraft assembly. Senior workers mentored junior ones, passing on techniques and tricks that weren't written in any manual. Engineers conducted regular inspections and maintained detailed records of defects, their causes, and solutions. This wasn't because Soviet workers were inherently more skilled or conscientious than Chinese workers. It was because the Soviet aviation industry had been building increasingly complex aircraft for 3 decades, learning painful lessons along the way, and developing organizational systems to prevent recurring problems. China was trying to leap directly from basic manufacturing to supersonic fighter production. The learning curve wasn't steep, it was vertical. Political pressure made it steeper still. Chinese Communist Party officials, inspired by Mao's vision of rapid industrialization and eager to prove that socialism could achieve what capitalism had taken decades to accomplish, pushed for aggressive production schedules. Factory managers who expressed concerns about quality or suggested slower, more methodical approaches to learning new techniques risked being accused of rightist thinking or lack of revolutionary enthusiasm. This political climate created enormous pressure to prioritize quantity over quality, to meet production quotas, even if it meant cutting corners or skipping quality control steps. We'll see exactly how catastrophic those shortcuts became when we examine the 1962 inspection findings. But first, let's follow the production timeline at Shenyang and watch things begin to unravel. The Shenyang Aircraft Factory, designated Factory Number 112 by Chinese authorities, became the center of Chinese efforts to produce the J-6. As the Chinese designated their version of the MiG-19, the factory complex, located in the industrial heart of Manchuria, had been established by the Japanese during their occupation and had some experience producing piston-engine aircraft based on Japanese designs. The buildings were substantial. The workforce was large and motivated. Chinese officials were confident that, with Soviet assistance, they could master jet fighter production within a few years. But jet fighters were an entirely different challenge from anything the factory had attempted before. Soviet advisors arrived starting in 1957 to oversee the technology transfer, bringing with them crates of blueprints, tooling specifications, and quality control procedures. The documentation alone filled several warehouses. Every part, every assembly procedure, every quality check was documented in meticulous detail. Soviet manufacturing practice emphasized documentation because they had learned that institutional memory was fragile. Workers retired, engineers moved to different projects, and without proper documentation, crucial knowledge could be lost. The Chinese received all of this documentation, translated into Chinese, along with Soviet-made tooling and gauges to ensure that Chinese-manufactured parts would match specifications. Initial production began in 1958 with what was essentially assembly of Soviet-supplied components. Chinese workers took major assemblies manufactured in Soviet factories' fuselage sections, wings, engine components, and assembled them into complete aircraft. This phase went relatively smoothly because the critical manufacturing had been done in Soviet facilities under Soviet quality control. The first Chinese-assembled J-6 flew in December 1958. Chinese propaganda celebrated this as a triumph of socialist industrialization, proof that China could master advanced technology and join the ranks of modern military powers within just a few years of the revolution. Newspapers published photographs of the aircraft, stories about dedicated workers, declarations that this was just the beginning of China's aerospace achievements. But behind the celebrations, serious problems were emerging, problems that Soviet advisors were documenting with growing alarm. As production shifted from assembly of Soviet components to manufacture of Chinese-made parts, quality began to deteriorate noticeably. The issues manifested in multiple ways across different aspects of production. Metallurgy was a fundamental problem. The aluminum alloys used in aircraft construction require precise composition and heat treatment to achieve the right combination of strength and workability. Chinese metallurgical facilities, struggling to meet ambitious production targets, sometimes produced alloys that didn't quite match specifications. The differences might seem smaller, few percentage points in alloying element content, a slightly different heat treatment temperature profile, but these small differences could significantly affect material properties. Wings that looked identical to Soviet-manufactured wings might have different fatigue characteristics, developing cracks earlier under operational stresses. Fuselage panels might be more brittle or less resistant to corrosion. Quality control, which Soviet factories had developed into a rigorous system of inspections and testing at multiple stages of production, was often treated in Chinese factories as an optional step that slowed production and made it harder to meet quotas. Factory managers, under intense political pressure to meet quotas set by party officials who often had no technical understanding of aircraft production, prioritized quantity over quality. Meeting the monthly production target was what got you recognized as an advanced worker and potentially promoted. Identifying quality problems that required rework or rejection of defective parts was seen as creating obstacles and potentially got you accused of sabotaging production goals. Workers who lacked proper training often improvised solutions when they encountered difficulties. And sometimes this improvisation led to serious problems. If a part didn't quite fit properly, instead of determining why and fixing the root cause, workers might force it into place or modify it on the spot to make it work. If a specified material wasn't available, they might substitute something similar without understanding how the substitution might affect performance. Senior Soviet advisor Anatoly Kuznetsov, in a report dated October 1959, documented finding fasteners that were supposed to be made of steel being fabricated from iron because the factory had run out of the correct material and nobody wanted to halt production to wait for proper supplies. These iron fasteners looked identical to steel ones, but were weaker and more prone to corrosion, creating potential failure points throughout the aircraft structure. The result was aircraft that looked correct on the surface, but contained hidden defects that could prove fatal in flight. Multiple Soviet inspection reports from this period describe remarkably consistent patterns across different batches of aircraft in different production periods. Welds that appeared solid on the surface but lacked proper penetration, creating weak points in the airframe structure. When Soviet inspectors began extraying these welds systematically after finding visible defects, they could see voids and incomplete fusion that weren't apparent from visual inspection. These defective welds might hold together under normal loads but could fail catastrophically under the high G forces of combat maneuvering. Hydraulic lines installed with fittings that weren't properly torqued. Soviet manufacturing procedures specified exact torque values for every hydraulic connection and required workers to use calibrated torque wrenches. Chinese factories often lacked sufficient torque wrenches, or workers didn't use them, consistently tightening fittings by feel. Some connections would be too loose, others over-tightened. The immediate result might be minor leaks, but over time improperly installed fittings could lead to sudden catastrophic failures. Electrical wiring that didn't follow proper routing. Wires need to be properly supported, routed away from heat sources and moving parts, and protected from chafing. Soviet inspectors found wiring bundles inadequately secured, allowing them to vibrate against structure and potentially wear through insulation. They found connectors not properly seated, creating intermittent electrical contacts that could cause system failures. They found wiring routed too close to hot engine components, where insulation could degrade and create short circuits or fires. By late 1961, Soviet advisors were sending increasingly urgent reports to Moscow. Something had to be done. The comprehensive inspection of early 1962 would confirm their worst fears. The breaking point came during a comprehensive inspection conducted by a Soviet technical delegation in early 1962. By this time, Sino-Soviet relations were already deteriorating over ideological disputes, Soviet reluctance to share nuclear weapons technology, and Chinese resentment of Soviet attempts to maintain leadership of the communist world. But cooperation on military projects continued, albeit with increasing tension and mutual suspicion. The Soviet engineers arrived at Shenyang expecting to review production improvements and possibly approve expanded manufacturing capacity. What Colonel Viktor Petrov and his team discovered over the following 3 weeks shocked them and violated every principle of Soviet aviation safety culture. Walking through the assembly halls, they found aircraft in various stages of completion that displayed workmanship far below any acceptable standard. Paint coverage was uneven, with bare metal showing in some areas and drips and runs in others, suggesting careless application. While paint might seem cosmetic, it's actually critical for corrosion protection. Uneven coverage indicates poor attention to detail that probably extended to more critical areas. They found protective covers missing from engine inlets, allowing dirt and debris to potentially enter the engines. They saw tools and parts left inside partially assembled aircraft, a cardinal sin in aircraft manufacturing because foreign objects left in an aircraft can cause catastrophic failures. A wrench left in a control surface cavity can jam controls. A rag left near an engine can be ingested during startup and destroy the engine. Deputy Chief Inspector Major Sergei Volkov later described the moment he found a hammer inside the fuselage of an aircraft marked ready for delivery. He showed it to the Chinese factory manager. The manager's response, translated through an interpreter, that must have just happened, wasn't there during final inspection. The hammer was covered in a layer of dust. When the delegation began detailed inspections of supposedly finished aircraft ready for delivery to Air Force units, using specialized equipment X-ray machines for examining welds, borescopes for inspecting internal areas, precision measuring tools, the situation appeared even worse. They selected several aircraft at random from different production batches and conducted thorough examinations. They found fuel bladders installed incorrectly, not properly sealed against the bladder bays, creating the risk of leaks that could lead to in-flight fires or explosive fuel-air mixtures in void spaces. In one aircraft, an aircraft marked ready for delivery to an operational Air Force unit, they discovered that the fuel bladder had been punctured during installation, then patched rather than replaced. A completely unacceptable practice. Control surfaces that didn't move through their full range because of binding in the linkages. The MiG-19's all-flying tail requires unrestricted movement to maintain control at high speeds. Soviet inspectors found aircraft where the horizontal stabilizer couldn't move through its full range, limiting the aircraft's pitch authority and potentially making it uncontrollable in some flight regimes. When they investigated, they discovered that linkage rods had been installed at slightly wrong angles, creating binding. The Chinese factory had apparently test-moved the controls on the ground and found them adequate, not realizing that airloads during flight would make the binding much worse. Engine installations revealed numerous problems where cowlings didn't fit properly, affecting cooling airflow and potentially causing overheating. Jet engines generate enormous heat, and proper cooling airflow is critical for preventing metal components from failing. Gaps between engine cowling panels can disrupt airflow patterns, causing hotspots. The Soviet inspectors found engine bays where panels had been forced into place rather than properly fitted, creating gaps and misalignments. They found fasteners missing or improperly installed. Most alarmingly, they discovered cracks in wing structures on aircraft that had barely accumulated any flight hours, suggesting fundamental problems with manufacturing techniques or materials. Colonel Petrov's team compiled a detailed report documenting over 400 specific defects across 12 aircraft selected at random from different production batches. When Chinese officials proposed that the Soviet visitors fly the J-6 fighters to experience their performance, Petrov declined. His reasoning, as recorded in the delegation's final report, was blunt. "I have a wife and 2 daughters in Moscow. I intend to see them again." The Chinese reaction was fury. Factory director Chen Wang accused the Soviets of deliberately undermining China's aerospace program, of refusing to acknowledge Chinese achievements out of jealousy or political spite. He insisted that Soviet standards were unnecessarily rigid and that Chinese manufacturing methods, while different, were equally effective. Some Chinese officials suggested that the Soviets were inventing problems to justify continued Chinese dependence on Soviet technical assistance and aircraft deliveries. The Soviet delegation returned to Moscow. Their report went directly to Deputy Premier Alexei Kosygin and Defense Minister Rodion Malinovsky. The incident became one of many factors accelerating the Sino-Soviet split. By 1960, Soviet advisors were being withdrawn from China. By 1963, the formal alliance between the two communist giants was effectively over. The truth, as available evidence from both Soviet and Chinese sources reveals, was more nuanced than either side wanted to admit publicly. The Soviet criticisms were largely justified from a technical standpoint. The manufacturing defects they identified were real and represented serious safety hazards. At the same time, Soviet advisors had failed to adequately appreciate the challenges China faced in rapidly building an aerospace industry from a limited industrial base. The rigid insistence on Soviet manufacturing methods, without sufficient adaptation to Chinese capabilities, and without patient long-term training programs contributed to the problems. Chinese factory workers weren't incompetent or careless. They were operating in a system that prioritized political campaigns over technical excellence, that rewarded meeting quotas over solving quality problems, and that lacked the decades of accumulated experience Soviet factories had developed through painful trial and error. But what matters most isn't who was to blame. What matters is what happened next when these aircraft went to war. The J-6 saw extensive combat service, primarily with Chinese-backed forces during the Vietnam War and later in various Middle Eastern and African conflicts. The aircraft's combat record provides the most revealing evidence of how manufacturing quality affected operational effectiveness, and the most tragic proof that the Soviet inspectors' concerns were justified. The combat record of the J-6 was mixed, reflecting both the improvements in later production batches and the fundamental limitations of trying to operate complex fighters without proper infrastructure and training. When flown by well-trained pilots and maintained by experienced ground crews, the J-6 could be effective. Its high speed and powerful cannon armament made it dangerous in skilled hands, but the aircraft's reputation for mechanical unreliability never entirely disappeared. Pilots who flew both Soviet-built MiG-19s and Chinese J-6 fighters consistently reported that the Soviet aircraft felt more solid, had better engine reliability, and demonstrated fewer unexpected failures. Pakistani pilots flew export versions designated F-6 against Indian aircraft during the 1965 and 1971 wars. Their experiences are particularly well documented. Squadron leader Muhammad Mahmud Alam, who became Pakistan's most celebrated ace, with claims of multiple kills in a single mission during the 1965 war, later provided candid assessments of the F-6 in interviews conducted after his retirement. Alam acknowledged the aircraft's impressive speed and devastating cannon armaments, 330mm weapons with a combined rate of fire that could destroy an enemy aircraft in a single burst. During the 1965 war, Pakistani F-6 squadrons achieved some successes against older Indian fighters like the Vampire, Mistar, and Hunter. The aircraft proved that it could be effective in combat when it worked. But Alam was equally frank about its problems. "We never fully trusted the engines," Alam recalled. "Compressor stalls happen far more often than with our American-supplied Sabres. You learn to listen for the warning signs, a slight change in exhaust note. If you caught it early, you might save the aircraft. If you didn't," he paused. "We lost good men to engine failures, not in combat." On routine training flights, another Pakistani pilot, Flight Lieutenant Imshi's Body, described the pre-flight ritual that F-6 pilots developed. "You would walk around the aircraft 3 times, checking everything you could see. Then you would sit in the cockpit and check everything you could reach. Then you would pray. Only then would you start the engines." Pakistani Air Force maintenance records from the period show F-6 squadrons struggling to maintain 50% operational readiness, meaning half their aircraft were grounded for maintenance or repair at any given time. This compared unfavorably with Soviet MiG-19 units, which maintained readiness rates above 70%. North Vietnamese pilots flew J-6 fighters against American aircraft, though they generally preferred the more refined MiG-17 or the superior MiG-21 when available. The Vietnam People's Air Force received its first J-6 fighters in the mid-1960s. North Vietnamese pilots were initially excited about operating a supersonic interceptor, but enthusiasm quickly gave way to frustration. Senior Lieutenant Nguyen Van Bay, one of North Vietnam's leading aces, flew the J-6 early in his combat career before transitioning to other types. In post-war interviews, Van Bay described the J-6 as powerful but unreliable, a tiger that might turn on you at any moment. He recalled an incident where his wingman's J-6 suffered a catastrophic engine failure during a training sortie. A compressor blade had separated almost certainly due to a manufacturing defect, causing such extensive damage that the pilot barely managed to eject before the aircraft disintegrated. The aircraft was in the air for less than 20 minutes. Another recurring theme in operational accounts concerns hydraulic system failures. Multiple pilots from different air forces reported incidents where hydraulic pressure dropped unexpectedly during high-speed maneuvering precisely when you needed controls most. In some cases, pilots managed to land safely using manual reversion mode, which provided direct mechanical linkage to control surfaces, but required enormous physical strength to manipulate at high speeds. In other cases, the loss of hydraulic pressure led to total loss of control and forced ejection or worse. The pattern of hydraulic failures suggests that the manufacturing quality problems Soviet inspectors identified in 1962 persisted into operational aircraft for years afterward. Egyptian Air Force Captain Hassan el-Badri flew both Soviet-built MiG-19s and Chinese J-6 fighters during the late 1960s and early 1970s. His memoir, published in 1985, provides the most detailed comparative assessment available in the most damning indictment of Chinese manufacturing quality. Egyptian pilots who flew both versions during the War of Attrition were particularly vocal about the quality difference. El-Badri's account stands out for its technical precision and emotional honesty. The Soviet MiG-19 was demanding but trustworthy, El-Badri wrote. You knew its limits. You knew what it would do. The Chinese J-6 was a different animal entirely. Same shape, same specifications on paper, but something was wrong in its soul. Every takeoff felt like gambling with your life. El-Badri describes an incident that nearly killed him. During a high-speed pass at low altitude, his J-6's canopy suddenly lifted, not shattering, but separating slightly from the frame. The noise and buffeting were overwhelming. He couldn't hear his own radio calls, couldn't focus on his instruments. He managed to slow down and land, hands shaking so badly he could barely taxi to the revetment. His wingman later told him that he had been screaming into the radio for nearly 2 minutes, not realizing his transmissions were going through. Investigation revealed that the canopy locking mechanism had been improperly assembled, missing a critical washer that should have prevented the lock from loosening under vibration. A washer, El-Badri wrote. A single missing washer nearly killed me at 800 kilometers per hour. He added a reflection that captures the psychological toll of flying unreliable aircraft. Every pilot develops a relationship with his aircraft. With the Soviet MiG, it was like a marriage, difficult sometimes, but built on trust. With the Chinese J-6, it was like riding a wild horse that might throw you at any moment. You never relaxed. You never trusted. That kind of flying wears you down mission after mission until you start making mistakes from exhaustion. The anecdotal evidence is compelling. Statistics are damning. Soviet Air Force MiG-19 units, operating from the mid-1950s through the late 1960s, experienced significantly lower rates of peacetime accidents and mechanical failures than Chinese J-6 units or export customers flying Chinese-built aircraft. While precise statistics are difficult to obtain due to the secrecy that surrounded both Soviet and Chinese military aviation data, analysis compiled from various sources reveals a stark pattern. When Soviet MiG-19 units experienced accidents, investigations typically attributed them to pilot error, combat damage, or operational factors like weather. Manufacturing defects as primary accident causes were relatively recurring in perhaps 5 to 10% of accidents, according to available data. When Chinese J-6 units or export customers experienced accidents, manufacturing defects appeared as primary or contributing causes far more frequently, possibly in 20 to 30% of cases, 3 to 6 times the Soviet rate. These manufacturing-related accidents included structural failures, engine failures traced to defective components, and system failures caused by improper assembly or substandard materials. Engine reliability showed the most dramatic difference. Soviet-built Tamansky RD-9B engines typically required major overhaul after approximately 200 hours of operation. Figure that. Soviet engineers gradually extended through incremental improvements in materials and manufacturing techniques. Chinese manufactured engines in early J-6 fighters often required major overhaul after 100 hours or less, with some engines experiencing catastrophic failures well before reaching even that limited service life. Turbine blade failures were particularly common in Chinese engines, suggesting problems with metallurgy, heat treatment, or quality control in the blade manufacturing process. Jet engine turbine blades are among the most demanding components in any aircraft, operating in extreme conditions that push materials to their limits. They require absolutely precise manufacturing to achieve acceptable reliability. The pattern of specific failures matched exactly what the Soviet inspection team had documented at Shenyang. Hydraulic leaks becoming sudden pressure losses. Electrical faults causing system failures. Structural cracks appearing in low-time airframes. The manufacturing quality problems identified in 1962 weren't corrected overnight. They persisted into operational aircraft for years, killing pilots who never knew what hazards they faced. After the Soviet withdrawal, China was left to solve its aircraft manufacturing problems independently, without Soviet technical support or quality control oversight. The process took years and cost lives. Without foreign technical oversight, Chinese engineers had to solve problems through trial and error process that was expensive, time-consuming, and sometimes deadly when failures occurred during flight testing or operational service. Chinese test pilots died in aircraft that probably wouldn't have been cleared for flight if Soviet quality control procedures had remained in place. Operational pilots died in accidents that investigation reports attributed to manufacturing defects that better inspection procedures might have caught. These deaths occurred not because Chinese engineers were incompetent or careless, but because they were working without the safety net of accumulated experience that the Soviet aerospace industry provided. Chinese engineers persisted. Production of the J-6 continued throughout the 1960s and into the early 1980s, with over 3,000 aircraft manufactured. The later aircraft produced after Chinese engineers had accumulated experience and developed their own quality control systems were significantly more reliable than the early examples that had alarmed Soviet inspectors. Senior engineer Liu Daxiang, who worked at Shenyang from 1963 until his retirement in 1991, later reflected on the transformation in a rare interview published by the Aviation Industry Corporation of China. "We had to learn everything the hard way," Liu said. "Every crashed aircraft was a teacher. Every failed component was a lesson. The Soviets couldn't teach us because they left. We taught ourselves through failure after failure until we understood." By the 1980s, Chinese aircraft factories were producing fighters that met international quality standards. The J-7, an improved version of the MiG-21, became a successful export fighter sold to multiple countries. Later Chinese designs like the J-10 and J-20 demonstrate sophisticated aerospace engineering and manufacturing capabilities that seemed impossible in those troubled years at Shenyang. The path from the J-6 factories of 1962 to modern Chinese aerospace industry represents one of the most significant industrial transformations of the late 20th century. But it was purchased at enormous cost in time and resources and in human lives. The political dimensions of the Shenyang inspection incident extended far beyond Sino-Soviet relations and influenced the entire trajectory of Communist bloc military cooperation. It influenced how China approached subsequent technology transfer agreements and shaped Chinese attitudes toward foreign technical assistance in ways that persisted for decades. After the Soviet withdrawal, Chinese leaders became intensely focused on achieving complete technological independence even when this meant accepting slower progress or inferior initial results. This self-reliance doctrine, while politically motivated by the humiliation of having Soviet experts criticize Chinese manufacturing and refuse to fly Chinese-built aircraft, had practical consequences for Chinese aerospace development that extended well into the 1980s and 1990s. The Soviet Union drew its own lessons from the experience that shaped its approach to military cooperation with client states for the remainder of the Cold War. Future technology transfer agreements became more restrictive, with greater emphasis on maintaining Soviet control over critical production stages and more intensive oversight of foreign manufacturing. The Shenyang incident became a case study in Soviet military academies and aerospace engineering institutes, cited as evidence of the challenges in transferring advanced technology to allies with limited industrial capabilities. Soviet advisors working with other client states from North Korea to Cuba to various Middle Eastern and African countries were instructed to pay closer attention to quality control and to be more assertive in halting production when serious defects were discovered, even if this caused political friction with host governments. The incident also influenced how Western intelligence agencies assessed communist bloc technology transfer and military capabilities. When the Shenyang inspection became known to Western intelligence through various sources including defectors and signals intelligence, It provided valuable insights into the real state of Chinese military aviation, despite propaganda claims of rapid progress. American and European intelligence analysts concluded that Chinese fighters, while numerous, were probably less reliable and effective than Soviet-manufactured equivalents. This assessment influenced Western military planning in Asia and affected how seriously Western military planners took the threat posed by Chinese air power during the 1960s and 1970s. From a broader historical perspective, the J-6 manufacturing crisis reveals fundamental tensions in technology transfer that remain relevant today. Transferring blueprints and equipment is relatively straightforward. Transferring the accumulated knowledge, manufacturing culture, and quality-controlled discipline that make complex technology work reliably is far more difficult. The Soviet engineers who refused to fly Chinese-built J-6 fighters weren't being irrational or prejudiced. They were recognizing a truth that modern aerospace companies still grapple with. Manufacturing jet fighters requires not just designs and tools, but an entire ecosystem of skills, standards, and institutional practices that take decades to develop. China's eventual success in overcoming these challenges makes the story more interesting, not less. The transformation from the troubled factories of 1962 to modern Chinese aerospace capability demonstrates what patient investment in genuine capabilities can achieve. But the story also carries warnings for those who try to shortcut the process. Multiple countries today are trying to establish domestic aerospace industries through licensing agreements, technology partnerships, or outright copying of foreign designs. The challenges they face, from establishing quality control systems to training skilled workers to building supporting industrial infrastructure, echoed the problems China confronted 60 years ago. Some countries are succeeding, following China's example of patient investment in genuine capabilities. Others are repeating China's early mistakes, prioritizing the appearance of progress over the substance of technical competence. The lesson from Shenyang is clear. You can copy a design. You can buy the equipment. You can even hire foreign advisors. But you cannot shortcut the long process of building true aerospace manufacturing expertise. The incident, when Soviet engineers refused to fly Chinese-built J-6 fighters, represents more than a footnote in Cold War aviation history. It encapsulates fundamental truths about technology transfer, manufacturing quality, and the gap between political ambition and technical reality. Those Soviet engineers standing on the tarmac at Shenyang, declining to fly aircraft they knew were potentially dangerous, were making a choice that resonates across decades. Colonel Viktor Petrov could have taken a diplomatic approach. He could have flown one mission, made polite comments, preserved the alliance. That's what political pressure demanded. That's what would have avoided the crisis that followed. Instead, he insisted that technical standards matter, that safety concerns cannot be dismissed for political convenience, that genuine expertise cannot be faked or rushed. His decision embarrassed China. It damaged diplomatic relations, contributed to the Sino-Soviet split that reshaped Cold War geopolitics, but it was the right decision. Flying those early J-6 fighters would have been genuinely dangerous, as subsequent accident rates demonstrated. The fact that China eventually solved its manufacturing problems and built a successful aerospace industry doesn't change the reality that in February 1962, those particular aircraft coming off those particular production lines were not safe to fly. Acknowledging that truth, despite the political costs, showed a kind of integrity that I find admirable, even as I recognize how it complicated Cold War alliances and contributed to diplomatic breakdown. The broader lesson is about honesty in technical matters, the importance of separating professional judgment from political pressure. In aerospace, as in many other fields, lives depend on maintaining standards and speaking truth about capabilities and limitations. The Soviet engineers at Shenyang did that at considerable political cost. Chinese engineers eventually learned to do that as well, though the learning process was painful and measured in lives lost. Looking at the specific technical challenges that plagued early J-6 production, several patterns emerged that remain instructive today. First, the problems weren't evenly distributed across the aircraft. The airframe manufacturing, while not up to Soviet standards, was generally adequate. The real trouble spots were the engines, the fuel systems, and the hydraulic controls, precisely the areas where precision manufacturing and quality control matter most. This suggests that Chinese factories had reasonable capabilities for structural assembly, but lacked the specialized skills and equipment needed for the most demanding subsystems. Second, many defects weren't immediately visible and only revealed themselves through detailed inspection or operational use. This explains why Chinese factory managers genuinely believed their aircraft were acceptable, while Soviet inspectors found them dangerously flawed. Without rigorous inspection protocols and testing procedures, it's easy to produce aircraft that look correct, but contain hidden problems. Third, the manufacturing issues weren't consistent across all aircraft, suggesting that individual worker skill and attention varied significantly. Some J-6 fighters were apparently well built by contemporary Chinese standards, while others were seriously defective. This variation itself was dangerous. Pilots never knew which kind of aircraft they were climbing into. Technical excellence requires more than knowledge and equipment. It requires a culture of honesty about problems, willingness to learn from failures, and patience to build capabilities properly rather than rushing to create impressive appearances. That's perhaps the most important takeaway from this story. Those lessons remain as relevant today as they were on that tarmac in Shenyang more than 60 years ago. If you found this deep dive into Cold War aviation history valuable, subscribe for more documentaries exploring the hidden stories of military technology. The next video examines another case where politics and engineering collided with deadly consequences. The story of a fighter never should have flown, and the cover-up that followed. See you there.